Okay, we are ready. Please.
All right. Hi, everyone. We've started the recording. This is a monumental day in the history of the course because we've been building up to this point where we actually do some machine learning modeling. Again, track the course repo, do frequent pulls. I usually remember, in fact, I don't think I've forgotten yet, to send a message in our pipeline class chat on our Slack work group when I've done a new push of the stuff that Gaita and I are creating. But there's an important addition to the README file right here, where we've added Jonathan's class repository to the main README file because he's doing such an amazing job tracking the lectures and giving us links to the videos and breaking down what we've covered in each session. So Jonathan, thank you so much for the way you're giving to our community this way. And you'll see we have a new directory in our course repo, which is Intro to Regression Modeling. I'm going to have some midweek sessions on Wednesdays. Again, send me a direct message, or I think if I haven't created it yet, I will create a channel on our Slack work group for that. But that way, if that time doesn't work for you, let me know. But that way, if Dr. Sommer, did you have a question?
No, thanks.
Very good. And Gio, help me if I miss a question. That way, by the way, I've been able to answer some questions just over Slack, so don't be afraid to use that, either the tech chat or the pipeline class chat. But let's briefly, I'm going to close these two files. I was presenting the same stuff to Omen this morning, and it was a good time. Let's go back to our fake data. Oh, and because we started late, Jonathan, let's try to do your presentation next time, but I'll show some cool stuff that's related to it. Sorry that we've missed that. We just had an unusual day. Notice that I've updated these a little bit. I did the lazy programmer type approach. I'm saying I just wanted a place where I could change the number of points rapidly for the fake data creation. And then I also made this divider so that it will always be the same scale. Basically, the number of points divided by 10, and that way I'm dividing X by that divider so that when I create X, it will always have the same range of numbers. The max won't get bigger. And then, but also I want to show you something fun. This was my version of what Jonathan and his friends were going to present this morning. I created this definition for a function of different types of noise that I could add in and scale my noise, my random noise. Now let's remember, this is a uniform distribution. It's not Gaussian. We could have put in Gaussian noise. We could have put in any type of distributed noise, but we're using uniform noise. And now I've got this set up to where I can scale it by a constant, by a linear function, by a sinusoidal. I could keep adding different functions, or I could even just have these as separate functions. But I just want to show you this one for fun. And so this will be different than what Jonathan would have shown. You see, this is sinusoidal.
Yeah. Which I'm not seeing the screen. I just see the Slack on your screen.
Oh, I shared I'm so sorry. I shared the wrong screen. It bum doped me. Hang on. Come on. Oh man. There we go. My bad. How? Oh man. I am trying to stop sharing and I'm struggling with the controls at the moment. This happens to me every once in a while. I do not understand why I'm not seeing the screen controls. This is frustrating. Oh, maybe for that reason? I have lost I cannot find my screen controls, and I don't know why it's being this way. You know what? For the sake of time, I am going to move that and this stuff out of the way for you. And then I'll just move this window over here and I will start again. Thank you, Jonathan. Again, I'll go back to what I was talking about earlier. Here's our updated repo. Here's our news section. And you can see that Jonathan's really good class repository tracking of our classes is here. This is where he's done that in his repo for us. Thank you again, Jonathan, for that. Sorry for that confusion. And then this is, I'll add some stuff for Colab too, but we're here. And then we want to be covering, I'll just shrink that for now. And this was the window I was talking through. Sorry for that. So I added one additional file to fake data. And Jonathan, thanks for pointing that out to me. These are different things I can return for a new function that is scaling my uniformly distributed noise. And this was what I was trying to say. This is centered between negative 0.5 and 0.5, the way I've got it set up here. But we could have put Gaussian noise in here or some other type of distribution noise. But now I'm scaling that noise by a function, and I just have different things on hand that I can scale that by. And if I do this funny sinusoidal one, which will be different from the ones you will present next week, that looks like this. So isn't that fun? In fact, this is more fun than we should be allowed to have. This is just showing what I was trying to say. We can put an envelope around our noise. And Jonathan and his little team that he's put together, they can show this more. But I'll just show you, what if I had done the heteroscedasticity? Well, and it's scaled too much. This is overscaled. But you can see here's where it should have been. And I just have the max set too high. So that's massive heteroscedasticity with too much max here. So if I change the max there to something more reasonable, like 0.5, it won't look so ridiculous. But Jonathan's going to present this in more detail, but just know that that file is there and you'll be able to see it. So that's something more reasonable. But I just wanted to give you a feel for, yes, you can just scale your noise within an envelope like that. So let's go over to fake data though, and close that. And so we've already played with this file. We've created the fake data. We've stored it here in lineardata.csv. So now I could load that. So I'm going to go to my second directory over here, and I'm going to open simple linear regression. Now this is the steep climb, everyone. Hopefully it's very pleasant. So I'm importing pandas. And is there a question? Okay, heard someone come off mute. Pandas as PD. This is just creating an alias, so I don't have to write pandas all the time. So when you see as, it just means, okay, let's use that alias. Then let's use this one for NumPy. Let's use this one for the random module of NumPy. And this is a big important one. sklearn model selection. We're going to just call that MS. So I'll highlight that when we get to it. We still have matplotlib's pyplot as plot. Now we have this new group called general tools. Well, what is that? That's right here in this new directory we created for the class. I'll open that, and I only have one function in there right now. It's calling scikit-learn's metrics and just calling it skl scikit-learn m for scikit-learn metrics and math. Why? Because we're going to print out our mean square error, our root mean square error, our mean absolute error, By the way, I get to move your beautiful faces back over here now. So it looks like I'm actually looking at you. Our median absolute error, then these are just errors. So basically, you'll see the line fit through noisy data, the model's predictions, and it'll be showing how big the error is from these different types of predictive errors. That's just comparing the actual data to the predicted data. And then R squared, which is for regression, is a very popular metric for model accuracy. And then adjusted R squared. Now, let's look at those real quick. R squared, it's worthwhile looking up the math for that. It's not overly complicated. It's just comparing the model error to the error that you would get if you used only the average. So the average is the baseline, and it's just looking at a ratio there. So that may not be accurate. But anyway, when we have a perfect model with no noise and it fits right through the data points, R squared would be 1.0. And we'll even show that at one point. Adjusted R squared, as you can see, is penalized in this denominator by the number of parameters that you use in your model. Now, I did this continuation trick. I realized just now I shouldn't do that. This is a cleaner way to do this in Python. Just wrap everything in parentheses, and now Python doesn't care that you're just going to continue this on the next line. And I do that so that things fit within here. So again, the general tools, we're importing that right here and just calling it GT. Now, the key part, the linear model portion of scikit-learn has a class called linear regression. We are importing that for usage. Okay, now we've talked through all the imports. Let's now go to loading the data. Notice that we're using pandas and its read CSV function. By the way, this is one of the great things about VS Code. Notice I didn't have to go to the Panda site to remind myself of all the calls or all the parameters I can use in the read CSV function. They're right here. But the only ones I need is say, hey, I don't want you to use the first row as a header, and we're going to load this linear data CSV file. And then I'm going to, after I load that into a data frame right here, I'm going to also name the columns X and Y. So let's do this. I've got this import sys here. The reason it's great is I haven't used that import yet. Well, I'm going to use it now. I only want to go this far for this point. And that's what I do. This is.
Sorry, you have a question from Pratik. The root square is different than.
I believe they are the same. One of the things about current data science, because data science as a field is still kind of young, at least in a way, and it's growing very fast. There's a fluctuation in the terminology, but I think that R2 score is probably the same as R squared. We will try to verify that. If someone could be so good as to save the chat, and then we can make sure we research some of these questions. Good question. Okay, so I'm going to run this much. Go ahead, Jonathan.
Sorry. Yeah, with the R2 squared as well, as you add more parameters, you will get a better score, but it's also misleading to inflation as you add those extra parameters, variables on the x-axis.
And that is why we use that R2 adjusted, because it will penalize for the parameters. Very good, thank you. Okay, so here we have our data frame, and true to Python, when we print a data frame, we're just printing it right here. It shows it kind of in the beginning and the end, and it shows the dimensions. So that's all good. Okay. And my wife is dealing with the dogs. It's part of our life. No worries, honey. Okay, so now all we're doing here is we're taking them out of data frame format and turning them into values. And so then we're just going to print those, but just for the sake of time, we'll still look at those. You see, I'm doing a lot of visualization throughout the process, but now I'm actually splitting that values array into X and Y parts here, and we'll look at those. And let's just go that far and look at this much. Okay, so up here, again, we have the data frame. Now we have the values in array format. Again, these are our features over here, and these are our labels, what we generated with our model and creating our fake data. Here's just our X values, which are 100 by 1, and our Y values, which are 100 of those. So now that we've done that, well, we have our data loaded, and that's good. But now we need to create training and test sets. Now, you've heard me emphasize many times the importance of doing cross-fold validation. That's where you can see from this that I'm going to use 1/4 of all my data for testing how good my model's working. But what we really want to do most of the time is give each fourth of the data a chance to be the test data, and then we train with all the other parts. We're just going to do one train test split today, but notice how we're doing this. This is one way you can do it. We've got our total point count by looking at our X, our features, and the shape 0 is just saying, how many of those do I have? It's looking at that dimension to get that as a number. Then I'm taking that total point count divided by 4, making sure it's an integer, and that's the number of test points that I want to create, 1/4 of the total points. Now, what I've done here with this range is I've said, okay, I want indices that range from 0 to 99 because I have 100 total points. So when I do that, I'm actually going to be creating random sets of indices from 0 to 99. Some of those indices will fall in the 0th part, the two groups. One, this is for the train, and this is for the test. So let's go that far and look at those indices. Okay, and I assume everyone's seeing this okay. Yes, exactly, Jonathan. That is correct. Why would you train with all of the other points and not just the fourth? Actually, we're training with 3/4 of the data, Kim, and we're testing with a fourth. And why? Because we want to make sure it all generalizes well. What is value of CV? I'm not sure on that one. Okay, but here again, these are the random indices we're using for our training and the random indices we're using for our test. Oh, in our seed is a way to just say your seed, it's a way you seed the random number generation routine. So if we wanted to change that each time, we could make sure we were getting new random variables each time we used it. That's the way I understand it. That may not be absolutely correct. But now that we've got that much, okay, now that we have those indices, I can actually define those indices for train and test. So see what I'm doing? I'm saying this is a great trait of NumPy. I can take those train indices and separate out those from X. For X train, the same thing for Y train, and then the other group here for X test and Y test. Okay, let's look at that much. and we're going to create this plot to see what we're looking at. Yeah, I think you are asking about cross-validation, and where did my plot is hiding? It is hiding. Where'd it go? Oh, I finally found my controls. They went over to a completely different monitor for some reason. My plot is hiding, and I don't know why. So I will close that one. Wait, yeah. Okay, let me try to rerun that and see if I can actually see the plot this time. They were showing up fine. There it is. It was hiding behind you guys. Okay, so what is this showing us? It's the blue dots are the training data and the red dots are the test data, and you can see they're fairly well interspersed. Okay, so now that I see that, okay, here's the big moment. We've been hiking. We're just coming over the edge of this beautiful view, and we're about to see some new amazing things. But it's such a big picture, it's going to take a moment to take it all in. We did the fit right here. Oh, sorry, I'm jumping ahead. We've just seen this plot of our training and test data. Now we're creating an instance of linear regression and just calling it mod, short for model. And one of the many parameters we could have used here is, this is tons of data here on this class, but one of the many parameters we can use is fit intercept, and we're going to say true there. And we're just going to fit the model using this. We're not going to really look at anything except what did you get for the intercept and what did you get for that one coefficient? What coefficient are we expecting? Something close to 2.0 and a 0 intercept, but it's not going to be perfectly that because we've got some sample bias. It's only 100 points, and a uniform distribution has an infinite number of points. So we're not going to see exactly 0 for the intercept and 2.0 for the coefficient, but we're going to see close. And then we'll use that model to actually make some predictions with X-test feature inputs. And then we'll print those metrics and look at a plot of the performance of the predictions. Okay. Wow. We're just about to the precipice of this beautiful overlook. Here we go. Okay. Now I'm hunting. There it goes. Okay. We're reviewing again our test and train data. So when I close that, the code will continue to run. Oh my, 99% accuracy. Isn't that insane? And look how low these metrics are. That's great. That's why we get this high value. By the way, I have to constantly review the math. I'm pretty sure what I told y'all about R squared is correct. And then I showed you R squared adjusted, but I have to review. Okay, so you can see, there it's fitting pretty well through that. And it really did mathematically minimize the error. But let's look. Oh, that is very close. Look at that. And look, that's really close to 0. So this is awesome. We did pretty good. Well, because now I hope y'all are beginning to see the value of creating fake data. I know what these parameters should be because I created the data with parameters close to these. But let's cheat, because that's what we do. We cheat in a helpful way, a good way, checking for questions. Can you explain again how it's creating the 4 sets? Oh, we're not doing cross-validation today, Karen. I was just explaining we're only creating one fold. We're only having a test set and a train set. But in actuality, we'd want each fourth of the data or each portion of the data that we picked for test to have a chance to be the test data. And then we would look not for the best accuracy, we'd look for a balance between the best accuracy and the best generalization, where the accuracy, the model we chose, the parameters we chose, worked really well across all the folds. But we're just not, we're crawling today. Seed generation, think of Minecraft world generation each time. That is a very good, it's not even an analogy, it's a reality. Yes, thank you. Okay, Karen, let me know if that didn't help. Oh, good. Thank you, Karen. Oh, for small data set, R square and adjusted will nearly be the same, I guess, as when we're adding new features, the R square won't. Each time we run this, that R squared will change a little bit because we're getting a new mixture of test and training data. It won't always be the same. So it'll change small amounts, but here's why I did that very lazy thing. I'm going to go up to 10,000 points. Why? Because I'm insane. Okay, anyway, just joking. It's no big deal because we get to create it ourselves. We didn't have to go out and collect this. And here is, boy, it just really likes hiding behind y'all. Trying to drag it over. There we go. Oh my. And the only way I can see that this is in fact data points, I'll zoom in right over here. Oh yeah, there's the data points. A portion of the 10,000 data points. So I'll close that. Now we have that new data. Well, now we can train using that. But instead of, now it'll be 7,500 for train and 2,500 for test. So let's run it. Okay, it keeps, I don't know why it wants to hide over here behind y'all. Okay, this gets so touchy. Can you see the red on top of the blue, everyone? Nod your heads if you can. Thank you. Okay. You can't see it, Greg? Oh, yeah, okay, good. I thought, anyway, yeah, it's a ton of data. Now it looks a little more clear. And let's do a fun zoom in again. Yep, there it's intermixed. Now let's let the rest of the model work, the rest of this file run. Okay, it created, I keep having to drag these over. Oh my, isn't that beautiful? Look how it put that line right in the middle. But more importantly, here's what I want to point out. I'll just keep that there. Oh, look how close we got to 0 and how close we got to 2 compared to the previous values. Okay, big bonus question. How does this relate to the central limit theorem? What did we just see? Okay, let me review the central limit theorem. Any type of distribution, if we randomly sample from it the same size each time and take the averages of those samples, now we do a histogram or a distribution of those averages, we will create a beautiful bell-shaped curve. That's the central limit theorem as we keep doing that. Now, how does that relate to what we just did? As we add more data from our population, as our sample gets bigger, as long as there's no horrible other types of bias in our data, we can, well, even if there is other horrible bias in our data, we can get a better and better fit. Now, this is, if we hadn't done it with fake data, we wouldn't see how we can approach what we know to be the ideal model. But if we were working with real world data, let me ask you this, can we know what the eventual real world model would be as we keep collecting data and fitting it? Can we know what that perfect model would have been? Okay, just in case you weren't sure, the answer is no.
No, because it's too continuous.
Yes, Jonathan. And we don't know what other biases are there. There's so many factors involved. So But notice we haven't been below, I think worst case, we might have gotten a high 98, which would have probably still rounded off to a 0.99. Now, again, this is fake data. Real world data is not this clean, but to drive home the point, now you can learn the principles better using fake data because we know what the ideal model was. We use that ideal model with noise injection to create this data so that we could see if our principles were working correctly. That's the only real reason we use the fake data, is to make sure the tool we're developing is working. And now I want y'all to appreciate where we're at. We imported modules for Python. We imported some data. It could be real world now. This could be real world data that we're bringing in. For simple things, we turned it into values. Now we're starting to format the data in a way that we can use it. We're splitting it into features and labels. In fact, I could have called them these. We're looking at those. We could have also just said dot shape, so we didn't have to look at these. That way we know the shape of the data. We're splitting into train and test indices. We apply those indices to create train and test data from our features and labels. We visualize that. You can never, well, maybe you can visualize too much, but no data scientist in their right mind would criticize you for that. And it'd be better to over visualize, is what I'm saying, than under visualize. Then we've actually finally, this is where we've been leading to. We fit the data. We have a model now. We have a y-intercept and other coefficients, and then we made predictions with that, and they worked. This is the starter file for the rest of your life when you need to do linear regression. I want you to plagiarize this repo. I want you to teach it to others. This is yours for life now. But this is the kernel. This is the beginning. By the way, on any simple problem that you could accomplish with linear regression, this is powerful. And now you can look at these model coefficients as we go to multiple variables, and you can see which feature is more important by looking at the model weights. Okay. I can see y'all are giddy with excitement. So I am going to close these two, and we're going to step into a little higher viewpoint on this beautiful precipice we've come to. This is simple regression engineered feature. So all that means is the same sort of thing, but the fake data that we had for this one was generated with something very similar. I need to go back here real quick, recreate this data. And I'll show you the plot. I swear this just wants to go right behind you guys, your pictures. Okay, so there's my new fake data we're working with here, or our fake data. I mean to share it with you. And here's the model part. Let me make this bigify it. Okay, I've got that fake data. I'm going to load it. That's the only change here. I'm loading this and I'm doing a few formatting changes. Here's one of them. I'm creating x0, which is just those x variables. The y variables have the curve in them because the model used x squared. So I'm doing some feature engineering. I might have added a lot of other engineered features like x. Well, if I had multiple features, but I could have added x cubed, x to the fourth, and let those be part of it too. But now I'm just doing some formatting to get this back to a combined vector. And we'll look at those here in a second. But everything else is really the same, except also for, everything else is exactly the same, except now I have two features, and one of them is not going to have a very high weight because it's not needed. So
I'm sorry.
Yes.
Sorry, you have two questions on the chat.
Thank you.
You're welcome.
So yeah, you do create the test and train data first, but not as it's as a way to ensure the model works. And then yes, as real as the other data was real too, Kim, but because you're training your models you would use for real work on real world data. But then you're right, you do the train test to make sure you've got a model that generalizes well. And then when new data comes in, you're predicting that other variable, the label, because it may be that we need to know a prediction of that variable before we can collect it. I hope that helps, Kim. We can revisit the question too, but right now, here's where we're at in the file. It's divided the train and test data up like we've seen before with the blue and the red. But then look what it did. Let's look at these together though. See how that first parameter for X is small? It used it a little bit. Why? Because of the sample bias. And boy, this is really close. And yeah, the y-intercept's not 0 like we hoped it would be, but it's very close. So, well, does this model have value? Let's say this was real world data. Does this model have value? Yes, it's 99% accurate. And would we have, if our data really did look somewhat like this, would we have to do cross-fold validation? Probably not. This is really good. By the way, anything over 0.5 is better than average. And do you want to use average for your predictions? No. Okay. Now let's go do something. Let's climb up a little higher. Let's go look at double feature linear data. So we've already seen this before. I'm going to dial this back to 100 points and recreate it. And this time we're going to have just to show you, there's our 3D data. And this is something I haven't shown you yet. I forgot that we've only seen Colab. Oh, I can make it bigger. I can make it full screen and I can rotate it. Now, gosh, a gold star to someone, I just find that it is horribly difficult to get the zoom to work in this. It just wants to keep rotating. So I think there's some trick to get the zoom to work in this, but yes. And thank you, Gio. Yeah, the general tools module is just our own module that there we go. I'm doing the right button and kind of dragging it. It's not perfect, but at least you kind of do a zoom in and it changes the tick values on the axes. So that's how I forgot that. Right drag. Okay. So I've recreated that data and I've seen the advantage of working from the IDE now. And so now I want to do a fit of that data. Let's see, I was looking at yes, okay. I'm just doubting myself. Okay, so we've recreated that fake data for double feature linear data. And again, what do we expect to see for our model parameters? We expect to see 2.0 and 4.0, but I think there's going to be a problem and I'm going to need to research it for y'all. Okay, this time we're going to load the data frame, but we have linear X1 and X2. We're not going to do any feature engineering. We're just going to use those two. And we're going to do the same things. There's certain areas where we have to format a little differently. Here, for example, by using this colon, it's saying use all columns, but only these indices for the X train. So that way it's getting X1 and X2. And then here, notice I'm not using a colon for Y. And so I also don't have to do the reshapes because of the way I'm doing this, but I do a reshape later. And I'll, by the way, take these files and play with them to your heart's content. Okay, so now let's run this and look at the piece parts. Okay, pulling the figure over. Isn't that beautiful? You can see the dots mixed together. It's quite instructive to get right in line here to see that, yeah, the noise is only in the Y direction. That's what that shows us right there. Okay, we'll close this. That's just presenting the X and, excuse me, the test and train set. And look at that. Isn't that great? We've got a really good fit model through those points. Yep. You can look at the line straight on if you're lucky. Usually gets blocked. And then, but isn't this interesting? I was expecting 4 and 2, and I got 3.2 and 1.6, and I got a y-intercept. And by the way, if we increase the number of points, this will not change. And yet we created the data with 2.0 and 4.0. Now what I'm doing here is full disclosure. I think this is some type of collinearity. I think that's why we're getting those model weights. But I will research that further and let you guys know, because, you know, fake models, they can do this to you. But otherwise, we did really good. This could still be useful. We didn't create any problems in the numerical solving with that likely collinearity. 1 second. Okay, so we have one last thing to do, obviously. That was pretty exciting, except for the collinearity mystery. We'll figure that out. So now let's make sure I didn't, yeah, this one's good. So I think this basically, and I can open the data double feature non-linear. Let's make sure, yeah, it looks like it's only 100 points, so that's good. So I'm going to just close that. So now I'm going to use, oh, I shouldn't have, yeah, the fake data. I'm squaring each to create the model. And so here's the corresponding model file in the second group, and I'll fit it. Again, the only changes, I've got Axis 3D. What I'm wanting y'all to appreciate is, now we'll look at ways to automate over how to automate checking out different models too. But I just want you to appreciate that this file is very similar to the other 3 files. We're doing slight changes. This is where most of the work comes in. Reformatting the data so that we can use, you notice I have x0 squared, x1, and x1 squared. We expect the coefficients for the non-squared features to be much smaller than the squared features. And again, the reason they don't go to the perfect model is because of the sampling bias. Okay, we're still seeding our NumPy random routine. We're still doing the model selection, train test split. We're still doing 1/4 of the data for testing. By the way, you could change that to 1/3 or 1/5. It's up to you. You could experiment with that too. Left as an exercise to the student. Okay, so then we do, we're going to look at the data. We're going to fit the data. And notice we're still using linear regression. Why is that? Because we're just handing it the features and we're saying, yeah, it'll just fit it accordingly. And I'll give you, for you that are hungry for the math details, I've got a fix for you. Okay, then we do the prediction, and I'm just going to run this whole thing. We'll look at the pieces along the way. Okay, here's our first plot, just to see that we did split into train and test. And then the next plot of the fit, oh my, look at that. Isn't that's more fun than we should be allowed to have, right there. And I'm going to just shrink this back a little bit, and let's go look at our parameters. Sure enough, we were looking for, let's go look at those again real quick. We were looking to achieve 0.1 and 0.2. 0.1, we didn't get quite to 0.2, but as we increase the amount of data, we'll see these arrive at 0.1 and 0.2. And this drive to 0. So I'll let y'all play with that on your own. Now I want to show you one other important thing. We've blazed through this. So what's your assignment? Play with this stuff. Play with it. How do you play with it? You go over to the fake data and you can generate different numbers of points, and you can use the ideas in this file, this variable. You can play with putting a function in for the envelope of that fake data. So like we did in number 5 on fake data. So this 3 could become a function basically. But all I'm trying to get at, you can play with the type of noise, you can play with different parameters, you can figure out if, as I suspect, we've got some collinearity going on, and that was what was causing us to not drive toward the parameters of the ideal model. You could figure out how to fix that, and I will try to present that very soon. But there's so much to play with. Why do you want to play? So you're learning to explore. Remember, this is the hiking analogy is very accurate. It's a spirit of, I'm going on a hike, I'm looking for the scenery. Every once in a while, I don't just keep hiking. We're at a beautiful point in the hike. We want to explore this scenery. Okay. Now, in the interest of time, I'm going to shrink that. I want to show you something real quick.
We have 5 minutes. Tom.
Yes, I'm trying to wrap up very rapidly here. Don't forget the old blog here. Look at these on a date basis. If you guys want to get into the details of the math and how to take that math to code, I would ignore this one for now. This modeling madness, do not look at that one. But if you wanted to look at this stuff, solving a system of equations, basic linear algebra tools, other linear algebra tools like determinant of a matrix, least squares math to pure Python. Then we put that in a module. Then machine learning module tools and polynomials. Guys, up to that point, all of that will describe the detailed math that you need for what we just went through. So you could actually do it, learn to do it even without those modules. So I just want to encourage you, yes, we were using the tools, but if you want to go deeper, I would go to those blog posts. And with that, we really do need to end here. I know you may have more questions. It looks like there weren't any more in the chat yet, but please, as you work through this, as you play, send me questions on the class chat, and the tech chat can be fair game too. But if it's about this stuff, try to reserve it for the pipeline class chat, and then send me a direct message with the email you want me to use to invite you to the Wednesday sessions for going over tech questions. And with that, I hope y'all enjoyed this. I hope it was I know I went fast. So if you guys want to go over this again, we certainly can. And I'll stop my share now that I finally found where that is. And Gio, you take over. And I guess we're just saying goodbye and seeing each other in mentoring, right? You are muted, but yes. Okay. Bye, everyone.
Yeah, I was telling in some few minutes. See you in the mentoring session. Bye.
Bye-bye.